we now want to know if we have, say, a dilute gas. Now again, a dilute ideal gas is a gas where, again, the intermolecular distance between gases or the gas particles are very far away from each other. So basically meaning that it's very large and that they only interact gravitationally. So we want to know what is what's known as the equation of state. So the equation of state is basically just a fancy way of saying what is the physical condition of my gas. So what are the things that I can actually measure? How would I describe this gas? Now, we're eventually going to look at this two separate ways. So the first way we're going to look at it, which is what we're going to do here, is to look at it macroscopically. So what do I mean by macroscopically? So basically what I mean is we want to look at it from an outside viewpoint and then look at what are properties that we can measure if we were measuring, say, a system which was full of the gas. So for example, let's say I have a box and I want to know what physical properties of this box could I measure. Now again, inside of this is my ideal gas. So I want to know what measurements can I make on the box to determine things about this ideal gas. So this is the first way we're going to look at it. The second way we're going to look at it is to now look at it microscopically. So what we want to do is go actually on the inside and talk about what is each individual atom or molecule doing on the inside of this box. So we want to look at this from more of a physics, more statistical standpoint, because again, this is all going to be statistics because this thing is going to be full with all kinds of different particles. We can't track each individual particle as it's actually bouncing around inside the box. So the only thing we can do is talk about, well, statistically, say on average, this particle is doing, etc. That's what's known as kinetic theory. We'll do that after we do this. So here, again, the only things we want to look at are what is the macroscopic version of the ideal gas law. So what are things that I can measure from here? So, well, if I look at the box, what are certain things I can measure from the box? Well, I could measure the volume of the box, right? So I can look at the size of this box, I can play with the volume of the box. I can measure its pressure, right? So I can measure the pressure. And finally, I can also measure the temperature. So again, we don't know what temperature actually is. Well, we do, I already told you, but don't worry too much about that. But again, all we know is it's something that says that this thing is in thermal equilibrium. So basically, from here we're going to do three different experiments. So experiment number 1, experiment number 2, and then finally experiment number 3. And then using these three different experiments, we're going to put together the ideal gas law. That was weird. Anyways, so the first way we're going to do this is we're going to look at this using constant temperature. So the first experiment we want to do is we want to see what happens if my system has constant temperature. Right? So, well here, basically what we're going to do is we're going to vary the size of the box and then, i.e. its volume, and then see what happens to the pressure. Or simultaneously, we'll play with the pressure and see what happens to the volume. So ultimately what we find then is that what if I plotted, let's say volume versus pressure, what we find is that we get a graph that looks something like this. Okay. So by looking at this, what we see then is that what pressure then is inversely proportional to the volume. So in this case, as the volume increases, the pressure goes down, or as the volume decreases, the pressure goes up. Okay. Now, another way to state this is that the pressure times the volume must be equal to a constant. This is another way to say that. One. So this is what's known as Boyle's law. So Boyle's law says that what? If we hold the temperature constant, what we find is that if we increase the volume of the box, so in this case, imagine I had like a piston here. So inside of here, I had half the size of the box, and then I move the piston out. And as I move the piston out, I increase the volume, the pressure of the gas on the inside actually goes down. So that is what's called Boyle's law. So the second experiment we're going to do is when the pressure is equal to a constant. So here we're going to fix the pressure, and then we're going to go ahead and play with the temperature and the volume. So here we find that what if we plotted, say, the volume versus the temperature, we actually find that there's a linear relationship between the two of these. We can draw that like this. So this tells me then that what? Temperature is directly related to volume. These two things are directly proportional to each other. This is what's known as Charles' law. So Charles' law says that, again, if we hold the pressure constant, if we then increase the temperature, we increase the volume, or simultaneously, if we, again, had a piston here, if I move the piston up, the pressure goes down, but the temperature increases. And finally, for the third one, here we're going to hold the last thing constant, which is the volume. So here we're going to hold the volume equal to a constant. And then we're going to play with the pressure and the temperature. So in this case, what we find is that what if I plot the pressure versus the temperature, what we again find is some sort of linear relationship between the two. So here, again, what we find is that the pressure is also directly proportional to the temperature. This is what's known as dilute's law. I think I'm pronouncing that right. So basically, Giesecke's law says almost the same thing that Charles' law says, but here it says that if we hold the volume constant, if we simply increase the pressure, the temperature is actually going to increase, or if we decrease the pressure, the temperature is going to decrease, and simultaneously. So from these three laws, which actually took like 100 years to actually do these three different experiments, that's another statement, we can then say that what? From here, we have the pressure that is inversely proportional to the volume, meaning that the pressure times the volume is equal to a constant. We have the temperature is proportional to the volume, and we have the pressure is proportional to the temperature. So from these three things together, this tells us then that the pressure times the volume then must be proportional to the temperature. Okay? That's the outcome of these three experiments. So this tells us then, at least for an ideal dilute gas, the pressure times the volume then must be proportional to the temperature. So here we just need some constants, constant of proportionalities, to make sure that this thing is dimensionally correct. So let's talk about each one of these. So here we're going to write this one of two ways. Either we're going to write the pressure times the volume is equal to write it this way, NKDT. We'll define these things in a second. And we also have that the pressure times the volume is equal to NR times T. Okay. So, great. What are these things? So N here is the number of atoms/molecules, depending on what my gas is actually made out of. So if it's made out of molecules, then this is going to be the number of molecules. If it's made simply of atoms, then it's going to be the number of atoms. Kb here is what's known as the Boltzmann's constant. Boltzmann's constant is equal to 1.38 times 10 to the minus 23 joules per Kelvin. We'll talk about why we know that's a joule here in a second. This one, little n here, is the number of moles. R is what's known as the universal gas constant. This thing has a particular value. Universal gas constant, for our purposes, is equal to 8.31 joules per mole per Kelvin. So how do I know this thing has units of joules? Well, let's look at the units of pressure times the volume. So for pressure, we know that's a Newton per meter squared times the volume, which is the same thing as a meter cubed. So the left-hand side then has units of newtons per meter squared times meter cubed, which is the same thing as a Newton times a meter, but a Newton times a meter is simply a joule. So the left-hand side has units of joules, i.e. units of energy. The right-hand side then has something times temperature, which means that this something then has to have units of what? Joules per temperature, and that's why this thing has, for here, units of joules per temperature. Reason for that is because molecules, we have no units associated with molecules, just number of molecules has no units. Where here, this has units of moles, that's why here we have to get rid of that moles. So what's the difference between these? This one is the physics version. This one is the chemistry version. Now, the important thing here is that these two things say the same thing. They both talk about the energy and the temperature, because again, P times V is simply the energy. So it's talking about the energy, but it's talking about it from two different perspectives. So in the chemistry version, what it's doing is it's talking about the energy per mole at a given temperature. That's what this thing is talking about. So all this means is that at a given temperature, this is on average the amount of energy per mole of the molecules or of the atoms. Now again, a mole is what? 6.02 times 10 to the 23rd molecules. So that's a big chunk or a big collection of molecules. The physics version, this is the energy per atom or the energy per molecule. So this one is talking about the energy per single atom or a single molecule that's actually floating around inside of my gas, where this one is actually talking about a collection or a mole worth of, or 6.02 times 10 to the 23rd, pardon me, number of atoms here. Now, these two things, again, have to tell me exactly the same thing. So whether I'm talking about a single atom or a mole worth of atom, these two things have to be equivalent to each other, which basically means then that what? These two expressions have to be the same. So here I get that N times KB must then be equal to N times R, which means that KB is then simply equal to what? N times R divided by N. But remember that a mole is equal to what? The number of molecules divided by Avogadro's number. So this is going to be the same thing then as what? R divided by Avogadro's number. So this is actually the definition of the Boltzmann's constant. So the Boltzmann's constant is actually the universal gas constant divided by Avogadro's number. But again, the point is that these things say exactly the same thing.